on the 14th of June, 2024. A team of researchers at the University of California, Los Angeles published a paper that shook the entire space science community to its core. The study, led by Dr. Salman Limoli and his colleagues at the Geffen School of Medicine, exposed groups of laboratory mice to simulated galactic cosmic radiation, the same type of radiation that would bombard astronauts during a journey to Mars. The exposure levels were carefully calibrated to match what a human crew would experience over a 7-month transit through deep space. What they found was terrifying. Within just weeks of exposure, the mice showed significant degradation of cardiovascular tissue. Their heart cells were damaged. Blood vessel walls were weakened. The inflammatory response in their bodies was elevated to dangerous levels. And here is the part that made headlines around the world. The damage was not temporary. It was permanent. The mice did not recover. Their hearts were fundamentally altered at the cellular level, and no amount of time reversed the destruction. Now think about this for a moment. This was just radiation. Just one single factor among dozens that Mars throws at the human body. Just cosmic rays alone, passing through the walls of a spacecraft as if they were made of paper, were enough to cause irreversible organ damage within weeks. Not years. Not decades. Weeks, and radiation is not even the most immediate threat on Mars. It is not even in the top 3 things that could kill you in the first few days. So today, I want to take you on a journey. A deeply scientific, thoroughly researched, and brutally honest journey through every single way that Mars is designed by physics and chemistry and biology to kill human beings. I am not going to sugarcoat this. I am not going to give you the inspiring Hollywood version of Mars exploration, where brave astronauts plant flags and make speeches. I am going to show you the reality that space agencies know about, that scientists have documented in thousands of peer-reviewed papers, and that somehow gets lost in the excitement of billionaires promising Mars colonies by 2030. In this video, you will learn why the soil beneath your feet on Mars is more toxic than industrial bleach. You will understand why a single breath of Martian air would kill you faster than cyanide. You will discover why the dust on Mars does not just cover your equipment, it actively eats away at your lungs from the inside. You will see why the radiation on the Martian surface is rewriting your DNA every single second, turning your own cells into ticking time bombs. You will understand why the psychological pressure of being trapped on Mars with no possibility of rescue could break the strongest human mind within months. And you will learn why all of these things happening simultaneously, compounding each other, feeding into each other, creating cascading failures in both your body and your technology, is what makes the first human Mars mission not just dangerous, but potentially a death sentence measured in weeks rather than years. Before we go any further, if you are someone who is fascinated by the deep science behind space exploration, if you want to understand the real challenges that nobody talks about in those flashy rocket launch videos, then do me a favor. Hit that subscribe button right now, turn on notifications, because this channel goes deep into the science that actually matters. And drop a comment telling me, would you accept a one-way ticket to Mars if someone offered it to you today? I want to know your honest answer. Now let us begin. To understand why Mars is so lethal, we need to start not on Mars itself, but in the space between Earth and Mars, because the journey to get there is already trying to kill you from the moment you leave the protective embrace of Earth. You see, our planet has a secret weapon that most people never think about. It is called the magnetosphere. Right now, as you sit watching this video, you are surrounded by an invisible magnetic bubble that extends tens of thousands of kilometers into space. This magnetic field, generated by the churning liquid iron core deep beneath your feet, acts like a force field against the most deadly particles in the universe. Every second of every day, particles from exploded stars, from the hearts of distant galaxies, from the violent surface of our own sun, are streaming toward Earth at nearly the speed of light. And every second of every day, our magnetosphere catches them, deflects them, channels them harmlessly toward the poles, where they create beautiful auroras instead of killing every living thing on the surface. The moment a spacecraft leaves low Earth orbit and ventures beyond this protective bubble, that protection vanishes. Instantly, completely, and the crew inside becomes exposed to something called galactic cosmic radiation. Now, I want you to understand what galactic cosmic rays actually are, because they are not like anything you encounter in everyday life. These are not like the X-rays at your dentist. They are not like the ultraviolet light from the sun that gives you a sunburn. Galactic cosmic rays are the nuclei of atoms, stripped of their electrons, accelerated to nearly the speed of light by supernova explosions and other violent cosmic events. We are talking about iron nuclei, carbon nuclei, oxygen nuclei, the cores of heavy atoms, traveling at 90% the speed of light or faster. When one of these particles hits you, it does not just pass through like an X-ray. It tears through your cells like a bullet through tissue paper. It shatters DNA strands. It rips apart molecular bonds. It leaves a trail of ionization damage through every cell it passes through. And here is the critical thing. You cannot stop them. Not really. They pass through the aluminum walls of a spacecraft as if the walls were not there. They pass through water shielding, through polyethylene, through every practical material we can put on a spacecraft. You would need meters of lead or concrete to stop the highest energy cosmic rays, and you simply cannot launch that much mass into space. NASA has measured radiation exposure on the International Space Station for over 2 decades. Astronauts on the ISS receive approximately 150 millisieverts of radiation per 6-month stay. Now, the ISS is in low Earth orbit, still partially protected by Earth's magnetosphere. The crew on a Mars transit would be in deep space with no magnetic protection for 7 months. The estimated radiation dose during Mars transit is 300 to 400 millisieverts or more, each way. And NASA's own career limit for astronauts is 1,000 millisieverts total lifetime exposure. Do the math. A single round trip to Mars uses 60 to 80% of an astronaut's entire lifetime radiation allowance just during transit, before they even set foot on Mars, before they do any actual work, before they spend a single day on the surface being bombarded by even more radiation. But galactic cosmic rays are the chronic threat, the slow killer. There is another radiation threat during transit that is far more acute and far more terrifying. Solar particle events. Our sun is a violent, unpredictable nuclear furnace. Periodically, without much warning, it erupts with massive solar flares and coronal mass ejections that blast billions of tons of energetic protons into space. These solar particle events can deliver potentially lethal radiation doses within hours if you are caught in deep space without adequate shielding. In 1859, a solar storm called the Carrington event hit Earth. It was so powerful that telegraph wires sparked and caught fire. If astronauts were in transit to Mars during an event of that magnitude, they could receive a lethal radiation dose in a single day. There would be nothing they could do. No emergency room. No evacuation. No shelter thick enough on a lightweight spacecraft. They would simply absorb the radiation and then deal with the consequences, which could range from severe radiation sickness to death within days or weeks. Now let me explain what this radiation actually does inside the human body, because understanding the mechanism is crucial to understanding why it is so dangerous. When a high-energy particle passes through a cell in your body, it damages DNA. Specifically, it causes what scientists call double-strand breaks. Your DNA is a double helix, two strands wound around each other. Normally, if one strand gets damaged, the other strand serves as a template for repair. But a double-strand break means both strands are severed at nearly the same location. This is catastrophic for the cell. The cell must now repair both strands simultaneously, and it often makes errors. These errors become mutations. Some mutations are harmless. Some cause the cell to die, which is actually a safety mechanism. But some mutations cause the cell to begin dividing uncontrollably. That is cancer. And it is not just cancer. The UCLA study I mentioned at the beginning showed cardiovascular damage. Other research has shown central nervous system damage. Cosmic rays passing through brain tissue can kill neurons outright, damage synaptic connections, and trigger neuroinflammation. Studies on rodents exposed to simulated space radiation show measurable cognitive decline within weeks. Memory impairment, reduced ability to learn new tasks, slower reaction times. Decision-making becomes compromised. Now think about this in the context of a Mars mission. At exactly the moment when astronauts need their minds to be at peak sharpness, when they are landing on an alien planet, when they are setting up life support systems, when they are making split-second decisions that determine whether they live or die. Their brains are literally being degraded by radiation passing through their skulls every second. The radiation is making them dumber, slower, more confused at the exact worst possible time. There is also immune system suppression. Multiple studies on astronauts returning from the ISS and on laboratory animals exposed to simulated space radiation show that radiation significantly weakens the immune system. T-cell function declines. The body's ability to fight infections is reduced. Dormant viruses that your immune system normally keeps in check can reactivate. Research published in the Journal of Applied Physiology has documented that astronauts on the ISS experience reactivation of herpes simplex virus, varicella zoster virus, which causes chickenpox and shingles, and cytomegalovirus. These viruses are present in most human bodies, but kept dormant by a healthy immune system. In space, under radiation stress, they wake up. On Mars, with even greater radiation exposure and no medical facility capable of treating viral outbreaks, a simple herpes reactivation could become a serious medical crisis. But radiation is not the only thing attacking your body during the 7-month transit to Mars. There is also the complete absence of gravity. In zero gravity, your body begins to change in profound and disturbing ways almost immediately. On Earth, your bones are constantly being stressed by gravity. Every time you stand, walk, run, climb stairs, your skeleton bears load. This mechanical stress is what tells your bones to stay strong. It triggers bone-building cells called osteoblasts to lay down new bone tissue. Remove gravity, and this signal disappears. Your bones begin to dissolve. Literally, calcium and minerals leach out of your bones and into your bloodstream. Your kidneys must filter this excess calcium, which is why kidney stones are incredibly common in space. Astronauts on the ISS lose approximately 1 to 2% of their bone density per month. Over a 7-month Mars transit, that means a potential loss of 7 to 14% of total bone density. And this is not evenly distributed. The bones that lose the most are weight-bearing bones. Hips, spine, legs, the exact bones you will need when you arrive on Mars and must stand, walk, and work in Martian gravity. Simultaneously, your muscles are atrophying. Without gravity to work against, muscles have no reason to maintain their mass. Even with the rigorous exercise programs on the ISS, where astronauts work out for 2.5 hours every single day. Muscle loss is still significant. Studies show that astronauts can lose up to 20% of their muscle mass during long-duration missions. And here is the cruel irony. When you arrive on Mars, you need to be physically strong. You need to set up habitats, carry equipment, perform construction tasks, do EVAs in heavy spacesuits. But you arrive at your destination in the weakest physical state of your life. Your bones are fragile. Your muscles are wasted. Your cardiovascular system has deconditioning because your heart has not had to pump blood against gravity for 7 months. The simple act of standing up on Mars could cause orthostatic intolerance, dizziness, fainting, or in extreme cases, cardiac events. And then there is the psychological dimension of the transit. For 7 months, you are confined in a spacecraft roughly the size of a large recreational vehicle with 4 to 6 other people. There is no privacy. There is no fresh air. There is no natural light. There is no variation in your environment. The same walls, the same people, the same routines. Day after day after day for over 200 days. In 2010, Russia and the European Space Agency conducted an experiment called Mars 500. 6 volunteers were sealed inside a simulated spacecraft for 520 days to study the psychological effects of long-duration isolation. The results were deeply concerning. Crew members developed severe sleep disorders. Some became effectively nocturnal, sleeping during the day and being awake at night to avoid interaction with other crew members. Depression was documented. Cognitive performance declined. Interpersonal conflicts emerged that required careful management. And this was a simulation. The participants knew they were on Earth. They knew they could leave in a genuine emergency. They knew they were not actually in danger. Real Mars transit crews will have none of these psychological safety nets. They will know, with absolute certainty, that if something goes catastrophically wrong, they cannot turn around. They cannot be evacuated. They cannot open the door and walk away. They are committed. And that knowledge, that inescapable awareness of total vulnerability, creates a psychological pressure that no simulation can truly replicate. There is also the communication delay. As the spacecraft moves farther from Earth, the time it takes for messages to travel between the crew and mission control grows steadily longer. At its closest, Mars is about 55 million kilometers from Earth. At its farthest, about 400 million kilometers. Light and radio signals travel at 300,000 kilometers per second. This means one-way communication takes between 3 and 22 minutes, depending on orbital positions. A round-trip conversation, sending a message and waiting for a reply, takes between 6 and 44 minutes minimum. This means no real-time communication, no phone calls, no video chats with family, no immediate guidance from mission control during emergencies. You send a message and then you wait. And wait. For 20 minutes, 40 minutes, nearly an hour sometimes. This is profoundly isolating in a way that is difficult to comprehend unless you have experienced true isolation. Astronauts can have near real-time conversations with their families. They can see Earth outside their window. They can be evacuated and returned home within hours if necessary. Mars transit crew has none of this. They watch Earth shrink to a point of light, a star among stars, and they know that everyone they love, everything they know, is receding at thousands of kilometers per hour, with no possibility of return for years. Now let us say they survive all of this. Let us say the radiation does not cause a fatal cardiac event. Let us say the bone loss is managed with exercise. Let us say the psychological pressure does not cause a breakdown. Let us say no solar particle event delivers a lethal dose. Let us say the spacecraft functions perfectly for 7 months. They arrive at Mars. And now, the real danger begins. Landing on Mars is something that NASA has called the 7 minutes of terror, and for good reason. Mars has an atmosphere, but it is terrible for landing. It is too thin to rely on parachutes alone like we do on Earth, but it is too thick to ignore entirely. A spacecraft entering the Martian atmosphere hits the upper layers at approximately 20,000 kilometers per hour. The atmosphere slows it somewhat, and a heat shield protects it from the extreme temperatures of entry. Parachutes help further. But for anything heavier than about 1 metric ton, parachutes alone cannot slow the vehicle enough for a safe landing. Every successful Mars landing to date has been a robotic mission. The heaviest thing we have ever landed on Mars is the Curiosity rover at approximately 900 kilograms, and that required the incredibly complex sky crane system that engineers considered almost insane when it was first proposed. A human mission requires landing 20 to 40 metric tons or more on the Martian surface. That is 20 to 40 times heavier than anything we have ever successfully landed there. The technology to do this does not currently exist in a proven, tested form. SpaceX's Starship is designed with this capability in mind, but as of early 2025, it has never been tested on Mars. It has never landed on any celestial body other than Earth. The first time this is attempted with humans on board will be, in a very real sense, an experiment. And if the experiment fails, if the engines do not fire correctly, if the guidance system makes an error, if the landing legs do not deploy properly, there is no abort option. There is no ejection seat. At the velocities involved, any failure means the vehicle impacts the surface at hundreds of kilometers per hour. Everyone on board dies instantly. But let us say the landing works perfectly. The spacecraft touches down on the Martian surface, the dust settles, the engines shut down, the crew is alive. They are on Mars, the first humans to ever set foot on another planet. And in that moment of triumph, the clock starts ticking, because Mars has been waiting for them. The first thing to understand about Mars is its atmosphere, or rather its lack of one. Stand outside on Mars without a spacesuit, and you will die in approximately 15 seconds. Not from the cold, although that would kill you too. Not from the radiation, although that is also lethal. You would die because the atmospheric pressure on Mars is so low that your bodily fluids would begin to boil at body temperature. This is a phenomenon called ebullition. On Earth, sea level atmospheric pressure is approximately 1,325 pascals. On Mars, atmospheric pressure is approximately 600 pascals. That is less than 1% of Earth's pressure. At this pressure, water boils at human body temperature. The moisture in your lungs, in your blood, in your tissue would begin to vaporize. Your lungs would not function because gas exchange requires pressure differential. You would lose consciousness in 10 to 15 seconds as your brain ran out of oxygen. Death would follow within 1 to 2 minutes. This is not speculation. This is physics. This is what happens to any unprotected human being at pressures below 6,300 pascals, known as the Armstrong limit. So everything about human survival on Mars depends on maintaining a pressurized environment. Your habitat is a pressure vessel. Your spacesuit is a pressure vessel. Every seal, every joint, every window, every connection point is all that stands between you and instant death. And here is where the engineering challenge becomes terrifying. Your habitat must maintain internal pressure of approximately 70 to 101 kilopascals. External pressure on Mars is 0.6 kilopascals. This means the pressure difference across your habitat walls is approximately 70 to 100 kilopascals. Your habitat is essentially a balloon that is constantly trying to explode outward. Every square meter of your habitat wall experiences approximately 70,000 to 100,000 newtons of outward force. That is equivalent to 7 to 10 metric tons pushing outward on every square meter. This enormous pressure difference means that any weakness in the structure, any degradation of seals over time, any impact from a rock kicked up by wind, any material fatigue from temperature cycling between day and night could result in a breach. And a breach on Mars is not like a slow leak you can casually patch. At that pressure differential, a hole the size of a coin would cause explosive decompression of a standard habitat in minutes. The air would scream out into the near vacuum outside. Internal temperature would plummet as pressure dropped. Anyone not in a spacesuit would lose consciousness within seconds. Now think about when this might happen. During the day, when everyone is alert and working, a breach is terrifying, but potentially survivable if emergency protocols are followed immediately. But what about at night? What about when the entire crew is asleep? A slow leak, a gradually failing seal, a crack that propagates over hours, could reduce habitat pressure below survivable levels before anyone wakes up. The alarms might sound, but cognitive performance upon abrupt awakening is poor. In the confusion, in the darkness, with pressure dropping and temperature falling, the margin for error is essentially zero. Let us talk about what is in that Martian atmosphere, the thin, nearly worthless atmosphere that provides almost no protection from radiation and almost no pressure, but is still present enough to be dangerous. The Martian atmosphere is 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, 0.13% oxygen, and trace amounts of carbon monoxide and water vapor. For comparison, Earth's atmosphere is 78% nitrogen, 21% oxygen, and only 0.04% carbon dioxide. Mars has almost no oxygen and is almost entirely carbon dioxide. Carbon dioxide is directly toxic to humans at high concentrations. Even at 1% concentration in the air you breathe, CO2 causes headaches, drowsiness, and impaired judgment. At 3%, you experience increased heart rate, difficulty breathing, and nausea. At 7 to 10%, you lose consciousness within minutes. At concentrations above 10%, death follows within minutes. Mars is at 95%. If your habitat seal breaks and Martian atmosphere leaks in, replacing your breathable air, you will die with absolute certainty. There is no level of training, no emergency protocol, no physical fitness that can help you breathe in 95% carbon dioxide and survive. This means that inside your habitat, you need active atmospheric management at all times. CO2 must be constantly removed from the air by chemical scrubbers. Oxygen must be constantly generated to replace what you breathe. The nitrogen and oxygen mix must be maintained at precise ratios. Temperature must be controlled. Humidity must be managed. Trace contaminants from off-gassing materials, from human metabolism, from equipment operation must be filtered out. All of this requires power, requires functioning machinery, and requires constant monitoring. The International Space Station has experienced numerous CO2 scrubber malfunctions over its lifetime. In 2019, CO2 levels on the ISS rose to levels that caused crew members to experience headaches and difficulty concentrating because the carbon dioxide removal system was underperforming. The crew reported symptoms. Mission Control worked the problem. Spare parts were available. The issue was resolved. On Mars, if your CO2 scrubber fails and you do not have a spare or cannot repair it, CO2 levels will begin rising immediately. In a standard habitat volume, without active removal, CO2 from human respiration alone would reach dangerous levels within hours, lethal levels within a day or two. And remember, on Mars, there is no resupply ship that can arrive in a few months. There is no emergency crew that can bring spare parts. You have what you brought with you, and that is all you will ever have until the next launch window, which comes only once every 26 months. Let me talk about oxygen generation, because this is perhaps the single most critical system for survival. In 2021, NASA landed the Perseverance rover on Mars, carrying an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE was designed to test whether oxygen could be produced from the Martian atmosphere by splitting carbon dioxide into carbon monoxide and oxygen. Over its operational period from 2021 to 2023, MOXIE successfully produced oxygen. This was celebrated as a triumph of engineering. But let us look at the numbers. Over approximately 2 years of operation, MOXIE produced a total of roughly 122 grams of oxygen. That is enough for one person to breathe for approximately 3 hours. A human needs about 840 grams of oxygen per day. A crew of 4 needs 3.36 kilograms per day. MOXIE at full output produced about 12 grams per hour. You would need approximately 12 MOXIE units running constantly to support a single person. Nearly 50 running constantly to support a crew of 4. And these units require electrical power, significant electrical power. And they have moving parts that wear out. And they operate in an environment filled with corrosive Martian dust. The alternative is bringing all your oxygen with you from Earth, or generating it through electrolysis of water. But water is also extremely limited and precious on Mars. Every molecule of water used for oxygen production is water that cannot be used for drinking, for growing food, for cooling systems, for cleaning. Everything on Mars is interconnected. Every resource has multiple critical uses. And every system that provides these resources is a single point of failure that, if it breaks, begins a countdown to death. Now let us go outside the habitat. Let us talk about the ground you would walk on, the soil you would touch, the dust that would coat everything you own. Because Martian soil is not just dirt, it is a toxic chemical weapon. In 2008, NASA's Phoenix lander touched down near the Martian North Pole and conducted the first direct chemical analysis of Martian soil. Among its many findings, one stood out as particularly alarming for future human exploration. The soil contained perchlorates, calcium perchlorate, and magnesium perchlorate at concentrations of approximately 0.5 to 1% by weight. Subsequent missions confirmed this finding. The Curiosity rover detected perchlorates at multiple locations in Gale Crater. The evidence suggests that perchlorates are globally distributed across the Martian surface. They are everywhere. Now, what are perchlorates and why are they dangerous? Perchlorates are salts containing the perchlorate ion, which is chlorine bonded to 4 oxygen atoms. On Earth, perchlorate contamination is a serious environmental and health concern, even at concentrations measured in parts per billion. In the United States, the EPA has set a health advisory level for perchlorate in drinking water at 15 parts per billion. 15 parts per billion. Martian soil contains perchlorates at concentrations of 5,000 to 10,000 parts per million. That is approximately 500,000 to 1 million times higher than the concentration that causes health concerns on Earth. What do perchlorates do to the human body? They attack the thyroid gland. Your thyroid is a small butterfly-shaped gland in your neck that produces hormones controlling your metabolism, energy levels, growth, brain function, and body temperature regulation. The thyroid needs iodine to produce these hormones. It actively absorbs iodine from your bloodstream. Perchlorate has a molecular shape similar enough to iodine that it competes with iodine for uptake by the thyroid. When perchlorate is present, the thyroid absorbs perchlorate instead of iodine. This blocks thyroid hormone production. The result is hypothyroidism, a condition where your body produces insufficient thyroid hormones. Symptoms include extreme fatigue, weight gain, cold intolerance, cognitive decline, depression, constipation, dry skin, hair loss, and in severe cases, organ failure. Now imagine developing hyperthyroidism on Mars. Extreme fatigue when you need maximum physical performance. Cognitive decline when you need sharp decision-making. Cold intolerance on a planet where temperatures drop to -73 degrees Celsius at night. Depression when you are already psychologically isolated beyond anything any human has experienced. The perchlorates in Martian soil are not just a theoretical concern. They represent a slow, insidious poisoning that would begin the moment astronauts start working with Martian soil or breathing air contaminated with Martian dust. And contamination is essentially inevitable. Martian dust particles are incredibly fine, typically 1 to 2 micrometers in diameter. For reference, a human hair is approximately 70 micrometers wide. Martian dust is 35 to 70 times finer than a human hair. It is finer than talcum powder. And it is electrically charged. Mars has no liquid water to settle dust, no rain to wash surfaces clean. The fine particles become electrostatically charged through interactions with other particles and with ultraviolet radiation. This electrostatic charge makes Martian dust cling to everything it touches with remarkable tenacity. It sticks to spacesuits, it sticks to tools, it sticks to habitat surfaces. It gets into joints, seals, and mechanisms. And most critically for human health, it gets carried into habitats on spacesuits and equipment whenever astronauts return from EVAs. We have direct experience with this problem from the Apollo moon missions. Apollo astronauts reported that lunar dust was extremely difficult to remove from suits and equipment. It was carried into the lunar module in significant quantities. Astronauts reported a strong smell similar to gunpowder when they removed their helmets. They experienced eye irritation, skin irritation, and respiratory irritation. Harrison Schmitt, Apollo 17 astronaut and a trained geologist, reported symptoms consistent with lunar dust exposure that he described as hay fever-like reactions. And lunar dust, while abrasive, is not chemically toxic. Martian dust is. Every EVA on Mars, every time an astronaut goes outside to do maintenance, conduct science, or repair systems, they will return to the airlock coated in fine Martian dust. Airlock procedures will attempt to remove this dust, but complete removal is essentially impossible with particles this fine and this electrostatically charged. Some dust will enter the habitat. It will accumulate in air filters. It will settle on surfaces. It will become airborne inside the habitat, and the crew will breathe it. Day after day, week after week. Each breath drawing perchlorate-laden particles deep into their lungs. But the chemical toxicity of perchlorates is not the only danger from Martian dust. In 2017, researchers at the University of Edinburgh published a study in the journal Scientific Reports that added another terrifying dimension. They found that when perchlorates are exposed to ultraviolet radiation, which is abundant on the Martian surface due to the thin atmosphere and lack of ozone layer, they become powerfully bactericidal. The combination of UV and perchlorates killed common bacteria within minutes. Further experiments showed that the addition of iron oxides and hydrogen peroxide, both present in Martian soil, increased the bactericidal effect by a factor of 10. The Martian surface is essentially a self-sterilizing toxic environment. For humans, this means that any biological material exposed to Martian soil in the presence of UV light faces rapid destruction. Your skin bacteria, the beneficial microorganisms that protect your skin from infection, would be killed on contact. Your gut microbiome, if somehow exposed, would face destruction. Any attempt to grow food in Martian soil without extensive processing would face this bactericidal effect. And there is yet another layer. Martian dust contains jagged particles of silicon dioxide, what we commonly call silica. On Earth, we know exactly what happens when humans breathe fine silica particles over extended periods. It causes silicosis, a serious and irreversible lung disease. Coal miners, sandblasters, and quarry workers develop silicosis from chronic silica exposure. The disease causes progressive scarring of lung tissue, reduced lung capacity, difficulty breathing, and increased susceptibility to tuberculosis and other lung infections. Eventually, severe silicosis is fatal. On Earth, silica particles have been weathered by water and wind over millions of years, rounding their edges somewhat. On Mars, there has been no liquid water for billions of years. The silica particles are freshly fractured, with sharp, jagged edges that cause more damage to delicate lung tissue than their Earth counterparts. Combined with the iron oxide particles that trigger inflammatory responses and the perchlorates that are chemically toxic, Martian dust represents a triple threat to the respiratory system. Mechanical damage from jagged silica, chemical damage from perchlorates, inflammatory damage from iron oxides, all simultaneously, all accumulating with each breath. The practical implication is stark. Even with the best air filtration systems, even with rigorous airlock protocols, some Martian dust will enter the habitat over weeks and months of EVA operations. The crew will be exposed, and the effects will accumulate. Within weeks, respiratory inflammation could begin. Within months, significant lung damage could develop. And there is no treatment on Mars. There is no clean room to escape to. There is no hospital for lung treatment. The dust is everywhere, and once it is in your lungs, it stays there. Now let us talk about radiation on the Martian surface, because the transit radiation was just the beginning. Earth is protected from cosmic radiation by two separate shields. First, the magnetosphere deflects charged particles. Second, the thick atmosphere absorbs most of what gets through. Mars has neither of these protections. Mars lost its global magnetic field approximately 4 billion years ago when its core cooled and solidified, stopping the internal dynamo that generates magnetic fields. Without a magnetic field, Mars was stripped of most of its atmosphere by the solar wind over billions of years. The result is a planet with no magnetic shield and a thin atmosphere that provides minimal radiation protection. The Curiosity rover carries an instrument called RAD, the Radiation Assessment Detector, which has been measuring surface radiation levels on Mars since 2012. The data is clear and concerning. The average radiation dose on the Martian surface is approximately 0.67 millisieverts per day. That translates to approximately 244 millisieverts per year. For comparison, the average person on Earth receives about 2.4 millisieverts per year from natural background radiation. Mars surface radiation is 100 times higher than Earth background. Now add this to the 300 to 400 millisieverts already accumulated during the 7-month transit. In the first month on the surface, you add another 20 millisieverts. Your total dose is climbing steadily toward levels where acute effects become likely and cancer risk becomes very significant. And remember, these are average numbers. They do not account for solar particle events. During a major solar flare, surface radiation on Mars could spike to many times the average level for hours or days. On Earth, our atmosphere provides the equivalent of 10 meters of water shielding overhead. On Mars, The atmosphere provides the equivalent of approximately 20 centimeters of water, nearly useless against energetic particles. A solar particle event that would be harmless on Earth could deliver dangerous radiation doses on the Martian surface within hours. The crew would need to seek shelter during solar particle events. But what shelter? Their habitat provides some shielding, but standard lightweight habitat materials reduce radiation by only 20 to 30% at best. The most effective shielding would be Martian regolith piled on top of the habitat, but this requires excavation equipment, significant construction effort, and time. Time that the crew may not have during the critical early weeks when they are weakest, most vulnerable, and most busy setting up essential systems. In those first weeks, they are likely living in their landing vehicle or a minimal initial habitat with minimal radiation shielding. Every day on the surface is another day of radiation accumulating in their bodies, damaging their DNA, weakening their immune systems, and degrading their cognitive function. Let me now address something that often gets overlooked in discussions of Mars radiation. It is not just the total dose that matters, it is the type of radiation. On Earth, most of our background radiation comes from relatively low-energy sources. On Mars, you are exposed to high-energy heavy ions from galactic cosmic rays. These particles deposit their energy differently than low-energy radiation. They create concentrated tracts of damage through tissue, causing clustered DNA damage that is much harder for cells to repair than the spread-out damage from low-energy radiation. Studies have shown that the same total radiation dose causes more biological damage when delivered by heavy ions compared to gamma rays or X-rays. This is quantified using a factor called the relative biological effectiveness, or ARB. For some galactic cosmic ray particles, the ARB can be 5 to 20 times higher than for gamma rays. This means that the actual biological damage on Mars may be 5 to 20 times worse than the simple dose numbers would suggest. And the DNA damage accumulates. Your body has repair mechanisms for DNA damage. Enzymes constantly patrol your chromosomes, detecting and fixing breaks. But on Mars, the damage rate exceeds the repair rate. Day after day, week after week, unrepaired damage accumulates. Cells with unrepairable damage either die, triggering the body to produce replacements from stem cells that are themselves being damaged, or they survive with mutations that could later become cancerous or lead to cellular dysfunction. Over weeks and months, this accumulating damage manifests as accelerated biological aging. Your cells age faster than they should. Your organs begin to show signs of degradation. By the time you have been on Mars for just a few weeks, your body has already been aged by years in terms of cellular damage. Now I want to bring all of these physical threats together and talk about something that might be even more immediately dangerous than any single one of them. Temperature. Mars is cold. Unimaginably, brutally, lethally cold. At the equator, which would be the warmest possible landing site, daytime temperatures on a good day might reach minus 20 degrees Celsius. At night, temperatures plummet to minus 73 degrees Celsius or lower. In winter, or at higher latitudes, temperatures can drop to minus 125 degrees Celsius. For reference, the coldest temperature ever recorded on Earth's surface is minus 89.2 degrees Celsius at Vostok Station in Antarctica. Mars regularly exceeds this at night across most of its surface. What does this mean for a human habitat? It means that heating is not optional. It is not a comfort feature. It is a moment-to-moment survival necessity. Without active heating, the interior of a habitat would cool to Martian ambient temperature within hours. At minus 70 degrees, human flesh freezes solid within minutes of exposure. Internal organs shut down. Blood becomes too viscous to pump. Death follows rapidly. This means your heating system must function continuously, 24 hours a day, 7 days a week, without fail. And heating requires power. Significant power. A pressurized habitat on Mars loses heat rapidly because of the enormous temperature difference between inside, approximately 20 degrees Celsius, and outside, potentially -70 or -100 degrees. Despite insulation, heat continuously radiates and conducts outward. The power demand for heating alone is substantial. Now combine this with the other power demands. Oxygen generation, CO2 removal, water recycling, lighting, communications, science equipment, life support monitoring systems, air filtration, all competing for the same limited power supply. And what provides this power? There are two options: solar panels or nuclear power. Solar panels on Mars receive only about 43% of the sunlight that reaches Earth's surface, because Mars is farther from the sun. So you need more than twice the panel area to generate the same power as on Earth. But there is a bigger problem. Dust storms. Mars experiences dust storms that can grow from regional events to planet-encircling global phenomena that last for months. During the 2018 global dust storm, sunlight at the surface was reduced by up to 99%. NASA's Opportunity rover, which had operated on solar power for 14 years, was killed by this storm. Its solar panels could not generate enough power to keep its heater running, and its electronics froze to death. Imagine a human crew relying on solar power when a global dust storm arrives. Their power generation drops by 90 or 99%. Suddenly, they cannot run all their life support systems. They must prioritize heating or oxygen, CO2 removal or water recycling, communications or air filtration. Every choice is between bad and worse. Battery backups might provide hours of full power, perhaps a day at reduced consumption. But dust storms can last weeks or months. There is no way to store enough battery power to survive a months-long global dust storm on battery alone if your primary power source is solar. Nuclear power, in the form of radioisotope thermoelectric generators or small fission reactors, is the alternative. Nuclear power is not dependent on sunlight and provides continuous output regardless of weather. But nuclear systems are heavy, complex, expensive, and have their own failure modes. RTGs degrade over time as their radioisotope fuel decays. Fission reactors require cooling systems, control mechanisms, and shielding, all of which can fail. And if your single nuclear power source has a critical failure, you are back to the same situation. No power. Life support dying. Temperature dropping. CO2 rising. The clock ticking. The temperature extremes create another engineering challenge that is less obvious but potentially just as deadly. Temperature cycling. Every single day on Mars, structures experience a temperature swing of 50 to 70 degrees Celsius between day and night. Materials expand when heated and contract when cooled. Over hundreds of these cycles, fasteners loosen, seals degrade, welds develop microscopic cracks, adhesives fatigue. This is called thermal cycling fatigue, and it is one of the primary failure modes for any long-duration structure in extreme environments. On Earth, we see this damage bridges, roads, aircraft and buildings over years. On Mars, the temperature swings are more extreme and more frequent. Habitat integrity could degrade significantly over weeks and months of thermal cycling. Seals that were perfect on day 1 may begin leaking on day 30. Structural elements that were strong on arrival may develop stress fractures by day 60. And inspection of these failures is difficult because they occur at the microscopic level initially, giving no warning until a catastrophic breach occurs. Let us now go deeper into the psychological dimension of survival on Mars, because the mind is ultimately what keeps everything else functioning. Every system repair, every emergency response, every routine maintenance task, every interpersonal interaction, everything that keeps you alive, depends on your brain functioning properly. And Mars attacks the brain from multiple directions simultaneously. First, there is the radiation we already discussed. Cosmic rays passing through brain tissue cause measurable cognitive decline. Research conducted at NASA's Space Radiation Laboratory at Brookhaven National Laboratory has exposed rodents to simulated galactic cosmic radiation and measured their cognitive function over time. The results show deficits in learning, memory, attention, and decision, making that persist for months after exposure. The damage to neural circuits appears to be permanent in many cases. Translated to a Mars mission, this means that the crew's intellectual capabilities are slowly degrading from the moment they leave Earth's magnetosphere. By the time they are on Mars, weeks or months into continuous radiation exposure, their cognitive function is measurably below baseline. They are literally not as smart, not as quick, not as capable as they were when they launched. Second, there is the isolation factor. No human being in the history of our species has ever been as isolated as the first people on Mars will be. This is not like being on a submarine, where rescue is possible. This is not like being in Antarctica, where aircraft can reach you. This is not like being on the ISS, where Earth fills your window and evacuation takes hours. On Mars, you are separated from all other humans by a minimum of 55 million kilometers. More typically, 100 to 400 million kilometers. Help cannot reach you for months or years. Evacuation is impossible. You cannot leave. Even if you have a complete psychological breakdown, even if you are sobbing and screaming and desperate to go home, you cannot go home. There is no mechanism to bring you back until the next launch window, which comes every 26 months. This is imprisonment without having committed a crime. And the awareness of this imprisonment, the knowledge that you are truly trapped, can break the strongest mind. Research on isolation in extreme environments provides some indication of what to expect, though nothing truly parallels the Mars situation. Studies of Antarctic overwinter crews, submarine crews, and isolation chamber experiments consistently show several phenomena. The third quarter effect is one of the most robust findings. Morale and psychological well-being tend to reach their lowest point approximately 3/4 of the way through an isolation period. For a Mars surface stay of approximately 500 days, the third quarter point would be around day 375. But psychological problems begin much earlier. Sleep disruption is typically one of the first symptoms, appearing within weeks. Mars makes this worse because the Martian day is 24 hours and 37 minutes long. This might seem like a trivial difference from Earth's 24-hour day, but research has shown that even small deviations from the circadian rhythm cause cumulative sleep debt and cognitive impairment. Over weeks, the 37-minute daily drift means your body clock is constantly fighting the Martian day length. Some crew members may adapt. Others may develop chronic insomnia, with all its associated problems of impaired judgment, emotional instability, reduced immune function, and increased accident risk. Interpersonal conflict is another near certainty. Psychological research on small groups in isolation consistently shows that conflicts emerge, escalate, and can become severe. In Antarctic stations, there have been documented cases of physical violence, withdrawals so complete that crew members essentially stopped communicating. And in one extreme historical case, a scientist at a Soviet Antarctic station reportedly attacked a colleague with an axe after a chess dispute. On Mars, with a crew of 4 to 6 people, personality conflicts have no buffer. You cannot take a walk to cool off. You cannot visit another friend. You cannot request a transfer. You are stuck with these same people in the same enclosed space for years. If interpersonal dynamics deteriorate to the point where crew members refuse to cooperate, the mission itself could fail. Life support maintenance, EVA safety protocols, and emergency response all require teamwork and communication. A dysfunctional crew is a crew at risk of death through operational failures. Then there is the phenomenon that psychologists studying long-duration spaceflight call Earth out of view. On the ISS, astronauts can always see Earth. It fills their windows. It is beautiful, close, and real. This visual connection to home provides a powerful psychological anchor. Astronauts on Mars will look up and see Earth as a bright star in the sky, a tiny point of light. All of humanity, everyone they love, everything they know, reduced to a dot barely distinguishable from the other stars. Research suggests this will trigger profound existential responses. A sense of cosmic loneliness, a feeling of disconnection from the human species, an awareness of the absolute void between you and everything familiar. Psychologists call this anticipated phenomenon Earth grief. It has never been experienced because no human has ever been far enough from Earth to experience it. The first Mars crew will be the test subjects. Compounding all of this is what I call the weight of knowing. Unlike explorers in previous centuries who could maintain hope, who could believe rescue might come, who could imagine being found, Mars explorers know exactly what their situation is. They have the scientific education to understand every threat. They can calculate the radiation damage accumulating in their bodies. They can monitor the degradation of their life support systems. They know the statistics, they know the probabilities, and they know that if something goes catastrophically wrong, they will die on Mars and their bodies may never be recovered. This constant awareness of mortality, this inescapable knowledge of vulnerability, creates chronic psychological stress. The stress hormone cortisol remains elevated, and chronic cortisol elevation suppresses the immune system, accelerates bone loss, impairs cognitive function, promotes cardiovascular disease, and disrupts sleep. The psychology literally makes every other physical threat worse. The fear of dying accelerates the dying. Let me now talk about something that rarely gets discussed in popular presentations about Mars, but represents one of the most practically terrifying scenarios. Medical emergencies. On Earth, we take for granted that if something goes wrong with our bodies, there is a system of care available. Ambulances, emergency rooms, surgeons, specialists, diagnostic imaging, pharmacies with thousands of medications, blood banks, intensive care units. On Mars, there is none of this. The nearest hospital is 55 to 400 million kilometers away. The crew will likely include one person with advanced medical training, not a specialist surgeon, not a complete medical team. One person with broad but limited training. Equipment will be limited to what could be packed and launched from Earth. No MRI machine weighing several tons. No full surgical suite. No blood bank. No pharmacy with thousands of drugs. A limited field medicine kit designed for the most likely emergencies, but incapable of handling the full range of what can go wrong with a human body. Consider appendicitis. On Earth, an inflamed appendix is a routine surgical emergency. Remove it and the patient recovers within weeks. The surgery takes about an hour. But on Mars, who performs the surgery? If the medical officer is the patient, who operates on them? There is historical precedent for this nightmare scenario. In 1961, Leonid Rogozov, a Soviet surgeon stationed at a remote Antarctic station, developed appendicitis. He was the only doctor. He performed an autoappendectomy, removing his own appendix while conscious, using a mirror and 2 assistants who held retractors and passed instruments. He survived. But he was a trained surgeon working in Earth gravity with sterile instruments. On Mars, the challenges are multiplied enormously. Surgery in 38% gravity means blood behaves differently, not pooling in wounds as expected, but forming floating droplets that obscure the surgical field. Anesthesia delivery must be adjusted for altered physiology. Wound healing is compromised by radiation damage to cells. Infection risk is elevated due to immune suppression. And post-surgical recovery requires rest, nutrition, and immune competence, all of which are compromised on Mars. Or consider a simpler scenario. A broken bone. After 7 months of zero-gravity transit, bone density has decreased by 10 to 14%. Bones are significantly more fragile than normal. On Mars, with 38% gravity, physical tasks are less strenuous than on Earth, but they still involve forces that fragile bones may not withstand. A fall during EVA, a heavy object dropped on a foot, a stumble on uneven terrain. Fractures that would be unlikely with healthy bones become plausible with space-weakened bones. And healing a fracture on Mars presents its own problems. Bone healing requires good nutrition, particularly calcium and vitamin D, both of which may be limited. It requires relative immobility of the fractured area, which is difficult when every crew member is needed for survival tasks. It requires immune competence to prevent infection, which is compromised. And research suggests that bone healing in reduced gravity is slower and produces weaker bone than healing in full Earth gravity. A fracture that would heal in 6 weeks on Earth might take months on Mars and might never fully regain original strength. Kidney stones deserve special mention because they are extraordinarily common in space. The bone density loss I described means calcium is constantly leaching from bones into the bloodstream. The kidneys must filter this calcium. In the process, calcium can crystallize in the kidneys, forming stones. Kidney stones are one of the most painful conditions a human can experience. On Earth, they are treated with pain medication, increased fluid intake, and if necessary, procedures to break up the stone. On Mars, pain medication may have degraded in the radiation environment. Fluid intake cannot be significantly increased because water is strictly rationed. And procedures requiring specialized equipment may be impossible. A large kidney stone blocking the ureter could lead to kidney infection, sepsis, and death. This brings up another critical issue: pharmaceutical degradation in the space radiation environment. A research study published in 2019 examined the stability of medications in conditions simulating long-duration space travel. The findings showed that many common medications degrade significantly faster when exposed to cosmic radiation. Antibiotics in particular showed reduced potency. Some medications became not just less effective, but potentially produced toxic breakdown products. On a Mars mission lasting 2.5 to 3 years, medications packed at launch may be significantly degraded by the time they are needed. An antibiotic that was fully potent at launch might be only 60 or 70% effective by month 18. This means infections become harder to treat. Already compromised immune systems cannot rely on full-strength pharmaceutical support. A simple infected wound, easily treated on Earth with a course of antibiotics, could become a life-threatening condition if the available antibiotics have lost their potency. And here is something truly frightening that has been documented on the ISS. Bacteria become more dangerous in space. Research published in the Proceedings of the National Academy of Sciences showed that Salmonella bacteria, grown in microgravity conditions, became approximately 3 times more virulent than the same strain grown on Earth. Other studies have shown that some bacteria become more resistant to antibiotics in space conditions. The mechanisms are not fully understood, but appear related to changes in gene expression triggered by the altered physical environment. On Mars, with reduced gravity, you have a scenario where bacteria are potentially more virulent and more antibiotic resistant, while the human immune system is suppressed and available antibiotics are degraded. This is a perfect storm for infectious disease. A minor bacterial infection that would clear on its own on Earth or respond easily to antibiotics could become a serious, potentially fatal illness on Mars. Let me now discuss the life support systems in more detail, because understanding how they work and how they fail is essential to understanding the timeline of death on Mars. Life support on a Mars habitat is not a single system. It is a complex web of interconnected systems that must all function simultaneously for the crew to survive. Air management handles oxygen generation, CO2 removal, trace contaminant control, temperature regulation, humidity control, and pressure maintenance. Water management handles water recycling from urine, humidity condensate, and wastewater, purification, storage, and distribution. Thermal management handles heating, cooling, and heat rejection. Power management provides electricity for all other systems. Waste management handles solid waste processing and potentially bioreactor systems. Each of these systems depends on the others. Water cooling loops keep electronics at proper temperature. Electricity powers the water pumps. Air circulation depends on fans that need electricity. CO2 scrubbers need both power and sometimes water. The interconnection means that a failure in one system can cascade into others.